Okay, so thank you to Lavinia and the other organizers for putting together this wonderful workshop and for the invitation. So I'll tell you about some results from this paper here, and then this one here in progress with Rachel Rosen, who is a postdoc alumni here in Stockholm. So this is about partially massless gravity, which is the special kind of graviton that lives on de Sitter space. And I want to talk about some general field theoretic features of it. So the partially massless graviton, it's interesting because of what it relations to the cosmological constant. But what I want to say really doesn't a priori have anything to do with the cosmological constant or cosmology as such. So the motivation, the underlying motivation is the cosmological constant problem, which you all know about. So the GRGT massive gravity, the class of theories that we just heard about from Claudia, theoretically they're consistent ghost-free effective field theories that propagate a single massive graviton degree of freedom and nothing else. So thought of as just an effective field theory around flat space with some strong coupling scale. There's nothing wrong with it. There's issues with superluminal propagation and analyticity of the amplitudes, which suggests that there's no standard local weakly coupled Lorentz invariant UV completion. I think Andrew will tell us later that it's actually already UV complete in some non-local sense. With regard to the cosmological constant problem, so the idea has always been that the acceleration of the universe is going to be explained somehow by the mass of the graviton. So there exists these self-accelerating solutions, and the hope is that one of these solutions can describe the acceleration that we see. And if you can manage to do this, if the graviton mass is of order the Hubble that we see today, then you've done better than the bare cosmological constant, because a small graviton mass is technically natural, it's protected from large quantum corrections because you have an enhanced symmetry as the mass goes to zero. As the mass goes to zero, you're restoring the diffeomorphism invariance of GR. And so quantum corrections have to be proportional to that mass itself. But what this doesn't tell you about is the old cosmological constant problem, why a large bare cosmological constant can't just be there from matter loops or whatever else, and why you wouldn't see that. So the massive gravity has less to say about that. You have to rely on some sort of degravitation mechanism, which hasn't really been shown to work for the full nonlinear theory. So to say something about this problem, you really need more, which the partially massless graviton promises. Okay, so as far as phenomenology and new signals and constraints and so on the massive graviton, these are all more or less related to the Weinstein mechanism that you need to hide this additional fifth force, which comes from the scalar mode, the fact that you have more degrees of freedom, and one of them gives you a fifth force in the linearized theory that you have to hide non-linearly, and then there's constraints and so on that you'll get from the requirement that this be hidden. Okay, so the partially massless graviton offers an opportunity to solve the full CC problem, because it essentially has a symmetry that sets the bare cosmological constant to be equal to the curvature of your de Sitter solution. In other words, it has a symmetry that forbids a bare cosmological constant. So if you could make this work somehow, you would be solving the old cosmological constant problem by some partially massless symmetry. The small acceleration of the universe would now be set by the small graviton mass. This small value still has to be put in by hand, but it's still protected. It's technically natural because you still have a larger diff symmetry that's present as the mass goes to zero. Furthermore, in this theory, as we'll see, there's no scalar mode. There's no fifth degree of freedom, so there's no need for there's no Weinstein mechanism, but there's also no need for it because there's no fifth force to screen. And along with that, there's no issues of superluminality or strong coupling, which are associated with this scalar mode.
Correct. Would the acceleration, self-acceleration be due to the lambda or due to the graviton mass?
Well, they're both
sort of
the same
so
in this theory.
So it's a combination of the two.
Well, you should think of them as they're both the same. There's a relation between them. The relation between them is fixed by the symmetry of the theory.
So if you give massive gravity, you have this lambda anyway.
That's right. Okay, so here's the basics of the linearized theory. So massive gravity on, let's look at a massive graviton. Here's the ordinary Fierz-Pauli massive graviton on a curved background. So H is the graviton, and then these covariant derivatives and so on are all due to the curved background with the curvature R. We can introduce the longitudinal Stuckelberg fields in the same sort of way that Claudia was talking about for the full theory, here just for the linearized theory. and do the sort of diagonalizations that you have to do, and you find this mess. And the thing to notice about this mess is that there's a special value of the background curvature relative to the graviton mass, where the scalar mode completely disappears from the action. Okay, so this is the partially massless tuning. So the scalar disappears at this special value. And what that means, if you trace back through the field redefinitions that were done, and the diagonalization and so on, that you have an enhanced gauge symmetry of the action at this point. Here's what the gauge symmetry looks like. There's a scalar gauge parameter, and this gauge symmetry is responsible for removing the longitudinal degree of freedom. So this is a theory which has only 4 degrees of freedom, unlike the full 5 degrees of freedom of a generic massive graviton. It's an irreducible 4 degrees of freedom. These degrees of freedom form an exotic representation of the de Sitter group, which has no flat space counterpart. Furthermore, it's stable only on de Sitter space, only if the cosmological constant of the background is positive. Okay, here's another way to see more transparently what's going on. So imagine we take a sort of decoupling limit where we imagine the mass of the graviton is going to 0, the background curvature is going to 0, but the ratio is held fixed. This is sort of like the Minkowski limit. Here's what the action looks like in that limit. And if we look at what's going on here, so here's the plane of graviton mass versus background curvature. So this limit is sort of zooming in towards the origin of this plane at various angles. If we look at the kinetic term of the vector mode, we notice that the kinetic term has to be positive, otherwise the vector mode is a ghost. So this whole negative m squared regime is ruled out. So in particular, there's no analog of the Breton or Friedman bound for spin 2 on de Sitter space, because as soon as the mass is negative, it's immediately unstable. And right at the boundary between stability and instability, we have an enhanced gauge symmetry where the vector mode disappears, and that's the gauge symmetry of general relativity, diff symmetry. If we look at the scalar mode there's a different line, and the scalar becomes unstable as we cross that line. So this is the Higuchi bound, and right where we saturate the Higuchi bound, that's where the scalar mode disappears, and we have the enhanced gauge symmetry of the partially massless theory. Okay, so this was the linearized theory. There's difficulties in finding an interacting theory. There's no known theory with a finite number of degrees of freedom that has this kind of gauge symmetry fully off shell. So if, for example, the DRGT massive gravity theories, none of them have this partially massless symmetry. Although it comes close. If you look at the theory that has sort of the right parameters that you'd expect to have this symmetry, there's a lot of curious features, which I'd be happy to tell you about if you ask me later, or I'm sure Fawad and his collaborators would be happy to tell you about all the interesting things that happen at this putative partially massless value, connections with conformal gravity and so on. But there's stronger statements than that, so that in fact there's no two-derivative consistent quartic interactions for the single partially massless graviton. So you're not going to be able to find an interacting theory just by putting together interactions for the usual graviton. And there's in fact no linear extension of the partially massless gauge symmetry itself, no sort of non-abelian extension, with one curious exception that you can read about in this paper. There's no stable interacting theory of a partially massless graviton and a massless graviton. So in particular, the bimassless, the bimetric theories don't have this symmetry. And if you try to get at a graviton with this mass from a Kaluza-Klein compactification of some higher dimensional theory, you also can never find this mass value in the spectrum because of some geometric bounds on the eigenvalues of internal manifold. So the one case I know of where you can do this is Vasilia-like theories, where you have an infinite tower of sort of higher partially massless spins. There, these things can exist. But those are very exotic and not clear how they would be phenomenologically relevant. Okay, so what I want to talk about are sort of other interesting field theoretic features of just the massless theory, sorry, just the linearized theory, which don't really have anything to do with cosmology or the cosmological constant a priori. In fact, this partially massless theory has a lot in common with just electromagnetism.
No, but sorry, what is the conclusion? The conclusion is that there is no theory. It doesn't exist.
No known theory. So I showed you what the no-go theory is.
Previous transparency looked pretty bad. So only negative evidence. So
Yeah, but these are the simplest things to try are the things that are shown. But there could be more complicated things you can imagine. You can imagine there's, yeah, infinite number of things you can imagine involving other degrees of freedom.
Question, cool. So in those, on the field transparency, what you meant by PM field was h mu nu.
Yeah, I mean a theory which has as its linearized limit
Yeah.
the partially massless theory.
So the
Right?
problem is that that equation does not even have general covariance.
That's right.
So it doesn't make sense to talk about finding a nonlinear completion of a field which is not consistent with general covariance.
Sure it does. I mean the ordinary mass of graviton is an example of that. The mass of graviton, if I write it in Fiertz polyform, doesn't have general covariance.
Yes.
But we're all talking about writing nonlinear versions of that.
Exactly, yes. So that one is okay. It turns out that there's a constraint that removes the groups and all that. But if you want to generalize a theory which is based on symmetries,
Yeah.
then you construct a theory with very nice partial matrix symmetry, but there is no general covariance.
That's right, but that's not, I mean, all that you need is for the symmetry to be preserved by the nonlinearities.
Exactly. So, but do you
General
even
covariance.
expect to get a theory of gravity with a very nice partial massless transformation which doesn't have general covariance?
I guess it depends, how do you define, what do you want gravity to be? How do you define gravity? Do you,
I
how do
want
you,
gravity to always have general covariance as a minimal condition.
well, then I don't know, because you can always reintroduce general covariance if you like through the Struppelbergs, but
Not
you
this
want
simple.
some sort of irreducible
Not this
general,
simple.
but then you're biased towards one, then GR, is it right? And GR is the only,
So if you look at the equation of the PM transformation, the transformation of h mu nu, on the right hand side you have an h mu nu which does not have any general covariance transformation. On the left hand side, on the right hand side you have a transformation which is a rank 2 tensor. So what I'm saying is that in that framework, it seems quite obvious that you should not be able to find a nonlinear generalization of PM symmetry.
to me that's not obvious,
Okay.
but, okay.
Thanks.
So, I mean, for example, Yang-Mills theory, suppose I knew nothing about GR or general covariance, and I just asked how do I complete a multiplicative vectors into a nonlinear theory. I would just do it ignorant of general covariance.
But there, at any stage, there is no conflict between your equation and general covariance, while the PM transformation is manifestly inconsistent.
Okay, that's the way I don't understand that point, but let's talk
Okay.
later. Yeah. Okay, okay, so this theory has many interesting features in common with just ordinary electromagnetism. It's a conformal field theory. It has full conformal invariance, invariance under the conformal isometries of de Sitter space, not just the ordinary isometries. It has no propagation, there's no superluminality or anything like that. The absence of these self-interactions that preserve degrees of freedom, it's the same for the photon. If I had asked for a theory of just a single photon that has two derivative interactions and preserves the degrees of freedom and preserves the symmetries, I'd find that you can't do it unless you introduce a multiplet like with the Yang-Mills theory. There's I'll show you in a second that there exists a one derivative field strength tensor that's analogous to the Maxwell tensor of ENM. And the property that I'll be focusing on is duality. It has a duality symmetry that's analogous to the electromagnetic duality of Maxwell's equations.
So conformal you mean ISO 3.2?
ISO 4.2 for 4 dimensions. Yeah, 15 parameter group of
That is
conformal transformations of
15
this.
parameter.
Yeah. Okay, so I want to review.
Sorry, but it's somehow non-linearly realized, right?
No, it's linearly realized.
Because there is a scale.
There's a scale, yes, but that's okay. I mean, there's
It's
still.
conformal and de Sitter, so it's a scaling algebra.
That's
So it's okay.
Okay, I want to review ENM for a second, so apologies if this insults your intelligence, but it'll be good to see the comparison of what's going on here with what's going on in the partially massless theory later. So we can think of ENM's, the gauge symmetry of ENM is based on a sequence of fields and a derivative operator between them. So we have a gauge parameter, which is a scalar. The gauge potential is a vector. The field strength, the Maxwell F mu nu, is an antisymmetric tensor. And then we have a Bianchi identity, which takes values in a antisymmetric 3-index tensor. And we have the exterior derivative operator that takes us between these various tensors. So these here are Young tableau, which you draw a box to represent each of the indices, and then the boxes and columns tell you that the indices are supposed to be completely anti-symmetrized. So we start with the scalar here. We have this D operator, which gives you the form of the gauge symmetry, which takes you to a vector. Then the vector takes you to the antisymmetric tensor, which is the expression for the field strength in terms of the potential. And then the derivative of the potential tells you the Bianchi identity that has to be satisfied by the field strength. And the crucial property of this sequence is that d squared equals 0, which tells you things like if the field strength vanishes, then the potential has to be pure gauge, or if a putative field strength satisfies the Bianchi identity, then it can be written in terms of the gauge potential. So, electromagnetic duality. So, Maxwell Lagrangian here, this F squared Lagrangian, has a global symmetry under U1, which is the duality transformation. This symmetry acts non-locally on the gauge field, but when you write it in terms of the field strength, it becomes local. So it transforms the field strength into its dual, which is just hitting the field strength with the epsilon tensor. And we can write the Maxwell equations in a duality covariant form. So the first equation is the field equation that you get from varying the action, and the second equation is the Bianchi identity that tells us that a field strength is written as a derivative of a potential. If we look at this in terms of the spatial variables, a space-time decomposition, we have electric field and we have the magnetic field. The magnetic field, we always learn about it as a vector, but it's more properly an antisymmetric tensor. It's only in 4 dimensions where you can dualize this antisymmetric tensor back into a vector. So it's only in 4 dimensions that the representation of the electric field and the magnetic field are the same. So in this dimension, you can have duality because you rotate the E field into the B field under the duality transformation. So the familiar Maxwell's equations are manifestly invariant under this replacement. Okay, we then try to add sources. So you can add electric sources by coupling to the gauge field in the action. And then the source appears on the right-hand side of the field equations, but it breaks duality invariance because it doesn't appear on the right-hand side of the Bianchi identity. So we're then invited to introduce magnetic sources in order to restore duality invariance. So if you introduce magnetic currents now, you can restore duality invariance if you postulate that the currents, the magnetic and electric charges, also transform into each other. But if you do this, the magnetic sources can't be introduced locally into the action because they don't couple to the original gauge field, they couple to the dual gauge field, which is non-locally related to the original gauge field. Okay. We then look for the simplest sources, so the electric and magnetic monopoles. So the basic electric source point solution is just the 1 over r Coulomb potential, or the 1 over r squared field strength. And the way we calculate the electric charge is to look at some Gaussian surface, a 2-sphere that surrounds the charge, and then integrate the dual of the electric field over it, and that gives us the charge. The monopole is the dual of this solution, and the monopole can't be represented by a gauge field everywhere. You need at least 2 patches, and you have to, so a patch covering the North Pole and one covering the South Pole, and you have to relate the 2 gauge transformations along the equator using some non-trivial gauge transformation. And then you calculate the magnetic charge by integrating the F over a Gaussian surface. Okay, so now we're gonna, and then there's a Dirac quantization condition, which comes from quantum mechanical considerations that tells you that the product of the electric and magnetic charges has to be 2 pi times an integer. Okay, so I want to replay this story for the partially massless graviton, and you'll see that everything more or less goes through analogous. So the partially massless graviton has an invariant, a gauge invariant field strength that looks like this antisymmetric combination of the derivatives of h mu nu, the graviton. And this, so these are the covariant derivatives with respect to the de Sitter background. And this field strength has a mixed symmetry, so it's antisymmetric in the first 2 indices, and this is how you draw the tableau for this symmetry. So the column means antisymmetric in the first 2, and then the other property it satisfies is that it vanishes if I try to antisymmetrize all 3 indices at once. You can check that this is invariant under the partially massless gauge transformation, which is a non-trivial statement because there's going to be cancellations between the non-commuting covariant derivatives and such. we can write the partially massless action in this f squared like form. And like electromagnetic duality, there's going to be a duality symmetry of this theory. So there's a global U1 symmetry of this free partially massless action, which again acts non-locally on the gauge field, but we'll see becomes local in terms of the field strength F.
Is that only for 4 dimensions? Or?
Yes, only for 4 dimensions. We'll see why. Okay, so the analogous construction of the gauge symmetry for partially massless goes like this. We have a scalar gauge parameter, phi. We have a potential now, which is the graviton, which is a 2-index symmetric tensor. We have this mixed symmetry field strength, and then we're going to have Bianchi identities that take values in some 4-index mixed symmetry tensor. So it looks like this. We have a D operator now, which the lowest order D operator takes you from a scalar to a symmetric tensor, which is the form of the gauge transformation. The next one is the form of the field strength, and the final one is the form of the Bianchi identity that the field strength has to satisfy. And the crucial property, you can show that d squared of this is 0, which is a non-trivial statement because these covariant derivatives here are covariant derivatives with respect to the background de Sitter acting on all the indices here. So there's non-trivial cancellations that go through to make this work. And because of this, you're going to have statements like if a field strength is 0, then it's pure gauge, and if the Bianchi identity is satisfied, then the field strength can be written as d over potential. Yeah, so the partially massless equations can be cast into a duality invariant form, and the way we do this is we start with a tensor which does not have the full mixed symmetry, but rather is a direct product of a pair of antisymmetric indices with a third vector index. So there's no symmetry yet among interchanging all the indices. And we define a dual field strength by dualizing over the antisymmetric pair of indices. We can now cast the field equations into the following set. So we have a set of field equations and a set of Bianchi identities, and within each one we have an algebraic equation and we have a differential equation. So the algebraic equation tells you that the trace of this tensor is going to be 0. There's only one non-trivial trace. And then the differential one is a Bianchi identity, that the exterior derivative with respect to these two antisymmetric indices should vanish. And we're going to have duality invariance now that rotates the tensor into its dual. Okay, so let's look at the algebraic, let's look at the Bianchi identities first. So the algebraic one tells you that this trace of the dual of the field strength has to be 0. If you write this out in indices and extract an epsilon, it's telling you that the fully antisymmetric part of this F tensor has to be 0. So this tensor started life as this direct product of an antisymmetric and a vector. Here's how it breaks up into a mixed symmetry representation and a totally antisymmetric part. So this Bianchi identity is telling you that the totally antisymmetric part is gone, and we're left with just the mixed symmetry representation that we want. Now we use this differential Bianchi identity and the fact that the d squared equals 0 for that complex, which tells us that F can be written in terms of the gauge potential. The field equations now, the algebraic field equation turns out to be equivalent to the divergence constraint of the partially massless field equations. And the differential field equations, upon using the divergence constraint, becomes equal to the partially massless field equations. Okay, so we can now break up into the analog of the electric and magnetic fields. So we do a space plus time decomposition. So this mixed symmetry field strength tensor that we start with, it breaks up into 4 pieces: a spatial tensor with mixed symmetry, a symmetric spatial tensor, an antisymmetric spatial tensor, and a vector. So you should think of, so the partially massless theory has a helicity 2 and it has a helicity 1 component. So this antisymmetric B here and this vector E, they sort of correspond to the electric field and the magnetic field of the helicity 1 part. And then the symmetric thing here corresponds to the electric graviton, and the mixed symmetry thing is like the gravitational magnetic field. But here, of course, it's all unified into a single representation. This split is not an invariant statement. So in 4 dimensions, and only in 4 dimensions, we can dualize the mixed symmetry guy and the antisymmetric B field into a tensor and a traceless symmetric tensor. So it's only in this representation that the magnetic degrees of freedom carry the same representation as the electric degrees of freedom. And the two now are interchanged by the duality invariance. So here's what the Maxwell equations look like in terms of the spatial parts. So this is what we would learn in undergraduate E&M class if the electromagnetic force were governed by this type of part.
I'm sorry, do you have interpretation for EMP?
The interpretation, I think, is just what I said, that it's like the electric and magnetic field associated with the helicity one part. Okay, so now if we talk about sources, so the partially massless theory is sourced by a partially conserved current, a T mu nu, which satisfies this partial conservation condition. And if we introduce such a current into the action, it will appear on the right-hand side of the field equations, but not for the Bianchi identity. So it will violate the duality invariance. So we're invited to restore the duality invariance by adding a magnetic stress tensor to source the Bianchi identities. We can now ask for the analog of the point charge solutions, the electric charge and the Dirac monopole that might exist in this theory. So this is what Rachel and I have found. There's an electric solution which looks like this in the static, this is written in the static de Sitter coordinates. And the thing to notice is that it depends on two parameters. There's a two-parameter family of solutions, and we'll see in a second what those mean. And there's a Dirac monopole-like solution, which looks like this. And just like the monopole, you need two different solutions, one covering the northern hemisphere and one covering the southern hemisphere, and they're joined at the equator by a partially massless gauge transformation. And again, it has two free parameters, C1 tilde, C2 tilde. Okay, so to understand what these parameters mean and how to count them, I have to say something about generalized global symmetries and what it means to have charges in a gauge theory. So the usual symmetries that we learn about in field theory are the nuller symmetries. The global symmetry is associated with global symmetries of a theory. So a usual nuller symmetry is a one-form symmetry. It's a current with one index that's conserved on shell. And we calculate a conserved charge by integrating the dual of that current over some free surface. So so conservation of the current is the same as the statement that the Q does not, the charge we calculate from this integral does not depend on small deformations of the surface. So the usual statement of this is that the charge is conserved. You take the surface to be a complete spatial surface at time t equals 0, and then you deform it by letting time flow. And the statement that it's independent of time is the statement that the charge is conserved. But it's more general than that. And we have another theorem which tells us that there's a one-to-one correspondence between non-trivial global symmetries and non-trivial conserved one-forms. Okay, so things like electric charge and magnetic charge are not of this form. The fact that electric charge is conserved is not because of a global symmetry like this. Rather, it's because of a generalized global symmetry, which is the existence of a two-form current, a current which is an antisymmetric tensor which is conserved on shell. And if we have one of these currents, the statement is that you get the conserved charge by integrating the dual of this over a two-dimensional surface rather than a three-dimensional surface. And that two-dimensional surface is the Gaussian surfaces that we're used to from electromagnetism. So the statement that the charge that this two-index generalized current is conserved is the same as the statement that the charge you calculate doesn't depend on the small deformations of this two surface. And now the generalization of Noether's theorem is that these on-shell conserved two forms, they're not associated with global symmetries, they're associated with reducibility parameters of the gauge transformation, which I'll say what those are now. So if you have a gauge theory, there can be certain gauge parameters for which the gauge transformation is 0. And that's what's known as a reducibility parameter. And there's a one-to-one correspondence between the reducibility parameters and these on-shell conserved two forms. So for example, electromagnetism, if we look at the gauge symmetry, it's dead. It's the usual one, and we look for functions phi for which the gauge transformation is 0, for which the field doesn't form. So the only solution is where phi is a constant. So there's one reducibility parameter in this theory, and the conserved 2 form that's associated with it is nothing but the field strength itself. So the conserved charge that we get is the integral of the 2 form, which is the familiar expression for the electric charge. It's the Gaussian surfaces that we like to integrate over. Another example, linearized gravity. So the gauge transformation for linearized gravity is linearized diffeomorphism. If we look for solutions, vector fields for which this is 0, that's nothing but the Killing's equation. So the reducibility parameters are just Killing vectors. And for each Killing vector, there's again a conserved 2 form. The expression is here. And the conserved charge associated with this is the ADM energy. If the Killing vector is your going in the time-like direction, otherwise it's the ADM angular momentum, or there's one of them for each Killing vector. And these are conserved, but they're expressed in terms of surface integrals rather than integrals over a space-like surface. Okay, so we have to ask the same question now for the partially massless theory. What are the analogs of the electric and magnetic charge that we get? So we need the reducibility parameters of the partially massless gauge transformation. And it turns out that the partially massless gauge transformation has 5 reducibility parameters, indexed by this capital I here, and they transform in the fundamental representation of the SO41 isometry group of de Sitter space. So you can think of these reducibility parameters as nothing but the embedding coordinates of the de Sitter space in some higher dimensional Minkowski space. So, for example, in static coordinates, this is what the embedding would look like. These functions are just the reducibility parameters. If I plug them into the gauge transformation, I'll get 0. Once we have these, we can calculate the conserved 2 form that's associated with them. So we now have 5 conserved 2 forms, which are conserved on shell. And so we have 5 electric charges that we can get by integrating over the 2 surface of this 2 form, and 5 magnetic charges that we get by integrating over the dual of the 2 form, which correspond to gauge transformations of the dual of the gauge field. Okay, so because of the fact that SO41 only has rank 2, there's only 2 independent such charges. In other words, whatever solution I have, there's going to be 5 charges. I can always do a de Sitter isometry to get down to 2 of them. So two independent charges, which will correspond to those 2 free parameters that we saw in the monopole solutions. And we expect a Dirac-like quantization condition between the electric and the magnetic monopoles if we were to try to quantize them. Okay, so here's, for example, how to calculate what these charges are for these monopole-like solutions. So here's de Sitter space. We take a spatial section like this. It looks just like a sphere. So our monopole-like solutions, they blow up at the north pole of the sphere. That's where the charge is localized. But they also blow up at the south pole of the sphere, because by Gauss's law, the total charge essentially has to be 0. So if you have a solution of a non-trivial charge up here, you have to have a compensating charge down here. So to calculate the charge, you would integrate over some 2 surface. For example, if you choose the 2 surface to be the equator, you can interpret this as calculating the charge either from the north pole or from calculating the charge from the south pole. So the 2 have to be equal and opposite. So here's one of the components of the field strength for our electric solution, and this plot is typical of all the components. So it blows up. This is the size of the component as a function of the longitude here. So it blows up at the north pole and also at the south pole, and is smooth everywhere in between. And if we calculate the 2 form on the solution, it has this characteristic form that shows you 1 over r squared. It's independent of the surface, and we calculate the charge, and we pick out exactly the C1. If we do this for the other charges, we can get the C2, and similarly for the magnetic charges. Okay, so in conclusion, these linear partially massless theories, they display many of the features of electromagnetism in terms of the structure of the gauge symmetries, and in terms of the structure of the point-like solutions and the duality. We've derived the analog of the Dirac monopoles that exist in the theory, but the structure of the charges is richer than ENM because there's many of them, and they transform non-trivially under the isometry group. So my my fantasy is that there should exist some Yang-Mills-like theory of this partially massless theories, that if I take a multiplet of them and try to couple them together, that it can be done so consistently, and that these monopoles should have some relevance to that. So for example, the Dirac monopole, it's a singular solution in the linear theory, but if you go to the nonlinear theory, if you deal with like the non-abelian Higgs model, that solution will be completed into the Polyakov monopole, which is smooth everywhere. So the singular solutions of the linear theory can tell you something about the smooth solutions of the full theory. So the hope is that there can be some Polyakov-like solution in the full theory that would reduce to this one in some sort of broken symmetry limit.
But you have to know the full theory. You
Yes.
have to have some heats or something like that.
That's right.
Is there anything you can say about the full theory from
You can say, I think all you can say is like the structure of these charges at infinity.
yeah,
So that's-
maybe it gives you a clue that there might exist some, you can extend your theory by extra degree.
Yeah,
Resolve it monopole, but still have to find it.
yeah.
In general, there is a not solution. There is a string and all that. Is it not related to?
Yeah, good. Yeah, that's related. So the top nut solution is one which you can think of as having magnetic gravitational charge.
Right, but it's still, the structure is similar. There is one bundle and then there is string and it's the same.
Yeah, that's right. Yeah, that's another example of a nonlinear version of these. Yeah, that is.
Is there a multi-gravity version of partial dimensions in analog to non-abelian theories?
Yeah, that's so. I don't know, but I hope, but I think that there should be. Based on these things.
Yeah, so it is a bit surprising that this duality business and so on works for the partial massless field instead of the massless field.
Oh, it works for the massless field as well.
So it works for the massless field alone also.
That's right. Yeah,
Okay.
linearized massless graviton also has a duality.
That's true, but I mean, okay. So is this exactly what you see? Is this the same that you see in your tensor sector, basically, or is it different?
It's different because the gauge structure is different.
Yeah, exactly. So because it's not the same gauge structure.
That's right.
Yeah.
It's different and it's more analogous to the electric case than it is to the gravitational.
So in massive electromagnetism or partially massless electromagnetism, we know that they are excluded by observation. So here, is there any observational signature that you could think that could lead to acceptance or exclusion experimentally?
Yeah, so I mean, first of all, to address any question like that, you need sort of the full nonlinear theory but the thought is that no, that this would be very similar to just a pure cosmological constant because you don't have this extra scalar degree of freedom that's giving you the new signatures. So the thought is that if this exists, it would really look like lambda CDM. It's just that it would be better theoretically because it would say why the CC is small.
Yeah, but what about, also, this would be okay for the case of perfect cosmological content, that we know that there have been times in the universe where cosmological content wasn't very, very important. Now, what happens, in a sense, this is really, the construction is very nice, but it's really tied to the very peculiar symmetry.
Right.
So once the symmetry is not anymore there,
Well, you'd imagine that if you could construct a theory that the symmetry should be there always.
always.
Yeah, there will be the symmetry, and then you have to couple matter to it in a way which respects the symmetry and so on. And if you can do that, then the early universe would be driven by matter in the same sort of way as the lambda CDM.
But it's true that it's not clear, it's not completely clear that when you couple to matter and it preserves that no symmetry, you don't also generate the equivalent of
You shouldn't. I mean, if
No, you won't generate a cosmological constant by the quantum corrections. You could generate something which would also.
I think that should be okay. If you can couple in a way which respects the symmetry, then it should be okay because.
It would generate something which also respects the symmetry.
Right, but it still has to be small because when mass goes to zero, you restore the full symmetry of GR. So the same arguments that you have for the ordinary massive gravity, the graviton can be
Right,
massless
but that
molecule.
doesn't necessarily exclude everything.
What do you mean by
So then, is it clear that you can't have, so you can't have a cosmological capacity? But in GR, I mean, in GR you have a cosmological capacity. So can't you be clear you can't generate something which would satisfy this, which would reduce to a cosmological capacity?
I think so, because I would think that something like that would violate this. I don't know, yeah, you really need a nonlinear theory to yes.
Okay, so related to the comment that Claudia made, I think, this symmetry is specifically four-dimensional.
The partially massless?
Yes.
Duality. No, the partially massless is not. It exists in.
Yeah, I mean, as far as we know, even in the case where things work, it's working in four dimensions.
Well, I think the things you do work only in four.
No. I mean, what other people do, not what we do.
No, the partially massless symmetry is.
Zenobia, with all, they have all these arguments that.
Oh, you mean the nonlinear bits? Yeah. The
Your paper.
Yeah. Sorry. I misunderstood. Yeah. So right. The nonlinear properties are better behaved in four.
Exactly. So that would very roughly kind of imply that in the quantum theory you will have an anomaly. Because if you can quantize either, but you have to regularize, either you do dimensional regularization, you put a momentum cutoff. In either case, you either go away from four dimensions or you break the scale. So it seems that there is no way of quantizing very roughly. There is no way of quantizing and choosing a regularization that respects your symmetry. And generically, when that happens, you generically end up with anomalies. Very hand wavy. So it's quite likely that Claudia said it might have quantum corrections.
But if you truly have an anomaly, then that's just the case where you don't have the symmetry. So
Quantum mechanics.
quantum mechanics. You would just say that the symmetry is
Still
not.
have more problem. Good question. So what would be your final aim? So the final aim would be that you get a nonlinear field, call it, say, I don't know, P mu nu, which on de Sitter backgrounds, when linearized, has a fluctuation which has h mu nu. Now when you look at the nonlinear theory with the P mu nu as a field, do you impose the requirement that that theory has to have general covariance?
No,
You don't.
I don't want that requirement.
Good.
This would look like more like a gauge.
Right. Yeah. Right. So the final theory, if it didn't have this, it would look more like a gauge theory than it does a gravity theory. I should also say, the Vasilyev theories, these higher spin theories, are based on this huge gauge group, which includes general covariance as a subset. But the full nonlinear theory looks nothing like general covariant theory. There's no limit where you can just get it to look like gravity interacting with other stuff. It's just one complete irreducible mess, which is what it is.
So can you see massive gravity in the Vasilyev construction?
There are constructions that give you massive fields, yes.
Just truncate that.
Oh no, yeah, there's no way to truncate just to that massive, as far as I know. There's no way to truncate just to a massive graviton and not the house. Same with the partial masses.
I think we had enough questions, so